The James Webb Space Telescope just delivered data that has scientists scrambling to rewrite our cosmic playbook. It didn't just map ancient galaxies. It mapped what may be the first detailed signs of the true edge of the observable universe. And what it revealed wasn't emptiness. It was structure, clusters, movement, and something even more intriguing. The universe may not be symmetrical. Okay, let me just say this straight. We thought the edge of the universe was just a limit in time, a blurry horizon. But now, there are indications in the data suggesting something is influencing us from beyond. Yes, NASA has effectively mapped the edge, and the map is not what cosmologists predicted for decades. The most surprising findings, the images flooding in from JWST, are challenging our understanding of cosmic evolution. Galaxies near the observable edge are forming faster and brighter than any models allow. These aren't just faint smudges of light. They're fully formed cosmic metropolises with metallicity and mass levels suggesting multiple generations of stars within just 300 million years of the Big Bang. Even more shocking, massive black holes are present almost immediately after the Big Bang began. One black hole discovered in galaxy UHZ1 already weighs between 10 and 100 million solar masses when the universe was barely 470 million years old. The Cosmos Web Survey, mapping nearly 800,000 galaxies in unprecedented detail, revealed something that left astronomers astonished. There are significantly more galaxies in the early universe than Hubble ever predicted. As Caitlin Casey, who co-led the Cosmos Web project, put it, the universe was producing a tremendous amount of light too early. It had only about 400 million years to form something like 1 billion solar masses of stars. We are still working to understand how this could happen. Some cosmologists now theorize that primordial gas clouds may have skipped star formation entirely, collapsing straight into black holes. This direct collapse theory would explain how such massive objects formed so quickly, but it requires us to rethink the universe's first chapters. Let that sink in. Galaxies formed faster than time should have allowed. It's like building a skyscraper overnight during a power outage. The edge isn't empty. JWST's groundbreaking mapping reveals something even more intriguing: density asymmetries at large redshift scales. The universe isn't just busier than we thought. It's uneven in ways that challenge our most basic assumptions. When these new findings are combined with earlier large-scale structure data, a pattern emerges. Analyses now suggest possible gravitational influences from beyond our observable edge. Something massive influencing the fabric of space-time itself. In one particular direction of the sky, galaxy clusters seem to be moving toward an unseen influence. NASA researchers track this motion out to at least 2.5 billion light-years, and the pattern persists. This shouldn't happen if matter is distributed evenly across the cosmos. What do you think is out there? Gravity from a hidden structure, or something even more mysterious? Share your thoughts in the comments. But that's just the start, because what JWST saw next in the cosmic microwave background could point to new insights about our universe. If you're fascinated by discoveries like these, consider subscribing for more cosmic updates. We dive deep into the mysteries space agencies are only starting to decode regarding cosmic structure. The Planck satellite detected puzzling anomalies years ago, a mysterious cold spot, and what scientists informally called the axis of alignment. temperature patterns that appear unusual in a perfectly uniform universe. Now, in a development that has cosmologists re-examining these findings, some of JWST's large-scale galaxy clustering patterns align with these very same anomalies. This correlation across different observing methods suggests we're not just seeing random noise. Multiple studies now indicate the universe may be slightly asymmetrical on cosmic scales. The Hercules Corona Borealis Great Wall, a structure spanning an estimated 10 billion light-years, challenges our understanding of how matter should be distributed. Imagine inflating a balloon, but one side stretches more than the other. That's what some scientists now believe may have happened during cosmic inflation. But if that were true, the implications for the shape of the universe are even bigger than you think. The impossible structures. Enter the Hercules Corona Borealis Great Wall. This isn't just a large structure. It's a cosmic behemoth that defies explanation. New measurements, completed in 2025, have confirmed its size at approximately 10 billion light-years. Let that sink in as a single structure spanning roughly 10% of the entire observable universe. Standard cosmology suggests this is highly unlikely. Gravity hasn't had enough time since the Big Bang to assemble something this massive. The basic models predict maximum structure sizes of about 1.2 billion light-years. Yet, here's something 8 times larger. As researcher Istvan Sapudi noted, our sample confirms a structure larger than expected, but we need more data to fully understand its implications. Its size challenges current models. Some researchers now argue this structure could only exist if inflation allowed power on larger scales than we predicted, essentially rewriting the rules of how the universe's initial fluctuations formed. Others suggest it might be a rare statistical anomaly happening to be in our field of view. A few theoretical physicists propose an even more speculative idea. Could it be a remnant from an earlier phase of the universe? But one observation may change everything, because upcoming telescope missions might provide further clues about the cosmos's large-scale structure. Time itself may not be consistent. When astronomers analyze the light from the most distant objects, they're literally looking back in time. And what they're finding is intriguing. Time dilation in some distant supernovae shows subtle deviations from predictions. Using light curves from deep field objects, researchers noticed small but consistent differences from what Einstein's relativity predicts. Events at the edge of the universe may not be unfolding at the rates our models expect. This led to speculation. Did time behave differently in the early universe? This could suggest expansion affects time in complex ways, a twist few models currently account for. If confirmed, it would force us to reconsider not just the structure of space, but the nature of time itself. The Hubble tension, the mismatch between early and late universe expansion rates, might be a symptom of this deeper complexity. The Planck satellite measured the current expansion rate to be about 67.44 km per megaparsec, but direct measurements give a higher value, around 73 km per megaparsec. This 9% difference might be telling us something significant. So the clocks at the edge of the universe may not be ticking like ours, and that means the further we look, the less we understand time itself As scientists grapple with these findings, several theories are emerging to explain what we're seeing. Some researchers have identified patterns in the CMB that may be topological relics like cosmic strings, essentially scars in the fabric of space-time from the universe's violent birth. These would be physical remnants from when space-time formed into the structure we now see, like cracks in cooling glass. The mysterious cold spot in the CMB, long a puzzle for cosmologists, is gaining new attention. While it could be explained by a large supervoid, some theorists suggest it might be a statistical fluctuation or a feature of cosmic inflation, though evidence for a colliding universe remains speculative. And there's more. Ancient gravitational waves from the first fraction of a second after the Big Bang may leave echoes we haven't detected yet. Future observatories, like LISA, could potentially pick up these primordial ripples, giving us a glimpse beyond even the CMB. These discoveries don't just change our models, they redefine our place in the cosmos. We thought the universe was mostly empty. Turns out, it may be more complex, interconnected, and dynamic than expected. The infant universe wasn't a gentle, slow emergence. It was a rapid, intense process that started almost immediately after the Big Bang. We used to think we lived in a universe that was average, unremarkable. But every new map tells us the opposite. We're in something strange, something active, and we may never fully map its boundaries. Now that we've seen how complex the cosmos is, let's step back and remember how we used to think about the universe. For decades, we've understood the observable universe to be roughly 93 billion light-years across. Not because it's 13.8 billion years old in each direction, but because space itself has been expanding. Objects we see at the edge today are much farther than 13.8 billion light-years away. The cosmic microwave background, that faint afterglow we can detect in all directions, formed about 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and light to travel freely. We've known about expansion rate disagreements, the Hubble tension, for years now. Measurements from the early universe suggest one rate, 67.4 hour km per megaparsec, while measurements of nearby galaxies give us another 73 km per megaparsec. Our standard model tells us the universe is comprised of approximately 5% ordinary matter, everything we can see, 27% dark matter, invisible stuff that affects gravity, and 68% dark energy, the mysterious force accelerating cosmic expansion. If you followed space science for years, you'll know the basics, but even those are being challenged now. The cosmic cliffhanger, UST, and the upcoming Nancy Grace Roman Space Telescope are just getting started. Roman will map billions of galaxies over thousands of square degrees, building 3D maps via both imaging and spectroscopy. What might we find as these missions continue? We could discover hints of early gravitational wave backgrounds, ripples in space-time from the universe's first moments that could reveal conditions we can't otherwise observe. We might find evidence of quantum limits to space-time, points where the universe's information capacity reaches fundamental boundaries set by quantum mechanics. And perhaps most profound, we may find signs that our universe is more interconnected than we thought, part of a larger cosmic structure. Each time we extend our reach farther, fainter, and in new wavelengths, we find the universe is more dynamic and unexpected than our prior models. The universe will continue to surprise us as we chart our place in this vast and fascinating expanse. Subscribe if you're ready for more, because what NASA is seeing at the edge is only the beginning.